When this airplane is fully loaded, it weighs over 300,000 kilograms, or nearly 750,000 pounds. Yet it gets off the ground with ease. Have you ever wondered how this is possible? You may already know that no object moves unless a force is applied to it. So there must be one or more forces that cause an airplane to move forward and to stay up in the air. Actually, there are 4 basic forces that act on every airplane in flight. The first is gravity. Gravity constantly pulls the airplane toward the ground. The second force is lift. Lift causes the airplane to rise. The forces of lift and gravity work in opposite directions. The third force is called thrust. Thrust causes the airplane to move forward. And the fourth is called drag. Drag includes everything that resists the airplane's forward motion, such as the friction between the airplane and the air it moves through. For an airplane to accelerate forward, thrust must be greater than drag. For it to accelerate upwards, lift must be greater than gravity. When the airplane is in steady, level flight, thrust is exactly equal to drag, and lift is exactly equal to gravity. But what produces the forces of thrust and lift? Thrust begins here with the fuel. Airplane fuel has stored energy called potential energy. Regardless of whether the fuel is burned in a propeller engine or in a jet engine, the potential energy of the fuel is changed in the engine, first into heat energy and then into mechanical energy. This mechanical energy from the engines produces thrust, the force which propels the airplane forward. But what produces lift? The force which overcomes gravity and allows an airplane to rise from the ground. To answer that, consider what the airplane flies in: air. You've probably seen that air that is not moving, static air, has no effect on objects in it. But what happens if the air between these balls is set in motion? Are you surprised? Instead of flying apart, as you might have suspected, the balls come together. This demonstrates a law of physics called Bernoulli's principle, which states that air pressure decreases as the speed of air increases. And in a similar manner, air pressure increases as the speed of air decreases. Here's another example. Hold a piece of paper by one end and blow across the top of it. The paper rises because the fast-moving air on top has less pressure than the air underneath. The force which elevates the paper is lift. Airplanes use the same principle. From this side view, notice that the airplane wing is not flat on top, but has a curved shape. Because of its shape, it's called an airfoil. An airfoil shape is used for all parts of an airplane which make use of air pressure to lift or control the airplane. What is air pressure? Air pressure is the force exerted by air on every object in the atmosphere. When an airplane is standing still, the air pressure is the same all over the wing. But when thrust is applied and the wing moves forward, air flows across the top and bottom surfaces. The distance from the front to the back along the curved top surface is greater than the distance across the bottom surface. Watch the air flowing over the wing. Notice that it has to travel farther in the same amount of time than the air going under the wing. Since it has farther to go, the air over the wing must travel faster than the air under the wing. You have already seen that as the speed of air increases, air pressure decreases. For this reason, there's less pressure above this wing than below it. The difference between the lower pressure above the wing and the higher pressure below the wing creates the force called lift. The greater the difference between these pressures, the greater the lift. Up to a certain point, lift is increased when the wing is tilted slightly upwards. This tilt is called the angle of attack. In flight, some of the air striking the underside of the tilted wing is turned back, around the front, and over the top of the wing in a long curving path. Because of its lengthened path, this air must flow extremely fast to rejoin the air moving a much shorter distance across the bottom of the wing. This great difference in speed increases the difference in the air pressure above and below the wing and greatly increases lift. And so a tilted wing can develop up to 10 times more lift than a horizontal wing. When the total lifting force overcomes the force of gravity, the airplane rises into the air. Once the plane is airborne, lift not only keeps it in the air, but also helps control its flight. To understand how the same pressure differences that produce lift can also cause the airplane to turn and dive and climb, you must look at some of the other basic airfoils. The tail section of this airplane is made up of two important symmetrical airfoils, the vertical stabilizer and the horizontal stabilizer. Notice the two movable control surfaces on the horizontal stabilizer. These are called elevators. When the elevators are moved up and down, they actually change the overall shape of the horizontal stabilizer. Now, watch what happens in slow motion. When the airplane is in flight and the elevators are lowered, air flowing over the curved surfaces of the airfoil creates a low pressure area on top and a high pressure area below the horizontal stabilizer. Thus, lift is developed. This lift pushes the tail of the airplane up, which in turn forces the nose down. When the elevators are raised in flight, the high and low pressure areas are reversed, so that the tail is forced down and the nose up. This control surface on the vertical stabilizer is called the rudder. The rudder can be moved to the right or to the left. When the airplane is in flight, which direction do you think the nose will move when the rudder swings to the left? Air flowing over the vertical stabilizer forms a high pressure area on the left side and a low pressure area on the right side. This difference in pressure causes the tail to move right, swinging the nose to the left. When the rudder position is reversed, the pressure difference is also reversed. So the tail swings to the left and the nose is pointed to the right. These two control surfaces on the wings are called ailerons. Notice that when one aileron swings down, the other swings up. A lowered aileron increases the lift of the wing, while a raised aileron decreases the lift. When the airplane is in flight, and the right aileron is lowered as the left one is simultaneously raised, the airflow causes the right wing to produce more lift than the left wing. So the airplane banks or tilts to the left. When combined with a rudder movement to the left, the airplane performs a bank turn. When the aileron and rudder positions are reversed, the airplane banks and turns to the right. And finally, these control surfaces on the wings are called flaps. The flaps slide back from the wing and at the same time rotate down. This is called lowering the flaps. It changes the shape and also increases the area of the wing. During takeoff, flaps are partially lowered to increase the lift so that the airplane can take off in a shorter distance. When approaching the runway for a landing, the flaps are again lowered so that even at very slow landing speeds, the wings produce enough lift to support the airplane. A slow landing speed is desirable because it permits the airplane to be landed on a much shorter runway. Since maximum lift is especially important on landings and takeoffs, airplanes normally take off and land against the wind. The wind increases the speed of the air over the wings and increases the lift. Since lift depends upon the amount and speed of the air passing over the wings, lift can also be increased by flying faster. Very fast airplanes often have short wings. Conversely, slower airplanes must have longer wings to produce enough lift. As the speed of the airplane increases, so does the drag. This affects not only the size, but also the shape of the wings. Airplanes designed to fly much slower than the speed of sound usually have straight wings. Straight wings are easy to control and produce a great deal of lift in proportion to their size. But V-shaped swept wings like these are better for high-speed airplanes because at high speeds, swept wings cause less drag than straight wings. Some airplanes, designed to fly at very high speeds, have wings which sweep back so far they form a triangle that looks like the Greek letter D or delta. Although delta wings perform very well at high speeds, they don't develop enough lift at low speeds to operate off short runways. Sometimes drag chutes are used to slow down the airplane after it has landed at high speed. To build airplanes that perform well at any speed, aeronautical engineers have designed wings which are movable, called variable sweep wings. At low speeds, the wings are spread out straight. As the airplane moves faster, the wings are swept back, until at very high speeds, they sweep all the way back to form delta wings. So no matter how fast the plane is flying, its wings form the best possible shape for that speed. The basic airfoils and control surfaces on most modern airplanes use these same fundamental principles to keep the airplane in the air and to control its flight. Although no one can be certain about how airplanes of the future will look or how they will operate, one fact will not change. Any airplane that has ever flown or ever will fly must reckon with the same four basic forces: lift and gravity and thrust and drag.